All right, morning again, students. So I said, we're gonna start transformation today, and transformation is my favorite topic in CSEC maths because it is the topic that you can do a question and know the answer. You can get a question to do, and you can know what the answer is going to be before you even do it. And when you're finished, you will know that the answer is correct. But in order for you to get to that level, there are some things that you ought to know. And the things that you're supposed to know are in that document that I gave you, that is called the transformation must know items. So if you take some time and make sure that you learn and know all those items, then when you get a transformation question to do in the exam, 99% of the time, you will know what the answer is before you even do the question. And even if you don't know what the answer is before you do the question, you will know that the answer is correct. You will know if the answer is correct when you're finished. All right? You can know what the answer is going to be before you even do a question in transformation. All right? So that's the beauty about transformation. Transformation also applies plenty matrices. And this is why we did the matrices topic first. So you really and truly have to know your matrices in order to do transformation. Another thing with transformation is that it is very, very close to function. It's almost like transformation is another way of doing functions. All right, just another way of doing functions. So if you understand functions and understand the things that we do in functions, then you can relate what we're going to do in transformation to those things. And then you'll appreciate transformation a lot easier, a lot more. All right, so it's a very easy topic, really and truly. All right, just that I think a lot of teachers teach it too close to the exam, and so the students don't get a lot of time to revise it in details. But because we are doing it now, we get a chance to revise it multiple times before the exam. The topic that we're doing after this one is vectors, and then after vectors, we're going to have some revision of everything that we did since we started in September, and then we're going to move on to trigonometry. All right, as we work our way down to complete in the syllabus by March, end of March, mid to end of March, we should finish the syllabus. All right, so I want to start this class by going through the matrices classwork. I think this topic, this matrices topic, is the one that I got the most results, most answers from in terms of persons doing the work, right? Which is a plus, but I'm still not yet at 100%. Right? I need 100% of the students to do the work, right? And it was particularly important that you do this classwork because, as I said, you have to know matrices in order to do transformation properly, and also to the vectors, right? Because you do some amount of transformation when you do vectors as well, right? Because you're gonna see the column vector a lot while doing vectors. So, you know, it's kind of important that you understand the matrices before we move forward to those topics. All right. So, as I always say, it's never too late for you to learn it properly anyway. So even if you did not do it, you still can do it even after I do it. All right. So I'm going to work these questions today to start the class, and then we're moving on to the transformation. All right. So question one, they gave us those two matrices, L and N. L and N. And they wanted us basically to just simply calculate this thing, L minus N squared. And the important thing is that we have to work out N squared first. And also to remember that N squared means, so N squared does not mean that you square the values in N. This is the N matrix, don't square them. And I didn't say anybody squaring them. Persons who did it, I didn't say anybody squaring them, which is good. So remember, the multiplication is a process that you have to carry out, where you multiply the rows of the first matrix by the columns of the second matrix. And so to do N squared, you have to put N beside N and then carry out the process. We're multiplying the relevant rows with the relevant columns. All right, so let's look at it over here. So for question 1, hold on a second. Oh, I need to close this first. Right, so for question 1, they gave us the L matrix is 3, 2, 1, 4. And the N matrix is -1, 3, 0, 2. And we want to find L minus N squared. We can just work it right here by putting the L matrix first, which is a 3, 2, 1, 4. And then we are subtracting N squared. But N squared is really N times itself. So we're subtracting the product. -1, 3, 0, 2, and multiplying that again by -1, 3, 0, 2. All right, and then we have to do this multiplication first. I think one student made a mistake and put a 3 right here. So sometimes, you know, these little mistakes are made. You have to keep careful. All right, careful and do a little check as you go. So that's supposed to be a 2. And then now, remember, you multiply the rows of the first matrix by the columns of the second matrix. As I said, I'm going to work this out first. So my next line is going to be that it is 3, 2, 1, 4. And I'm going to be subtracting the 2 by 2 matrix that I'm going to get from that with 4 values. All right. And we spent a lot of time going through the procedure. And as I said, persons who did it, generally speaking, got it right. So this first element that we want is in the first row and the first column. So multiply this first row by this first column. First element by first element, second element by second element. All right, so it's -1 times -1 and 3 times 0. -1 times -1, 3 times 0. -1 times -1 is 1, 3 times 0 is 0. That's the first value. And this element here now that we want next is in the first row, second column. So we use this first row with this second column to get that element. First element by first element, second element by second element. All right, so that's what we're going to do. All right, so let's do it. So it's -1 times 3 and 3 times 2. -1 times 3 and 3 times 2. -1 times 3 and 3 times 2. -1 times 3 is -3. 3 times 2 is 6. So you're adding 6. That's that. And this element here now is the second row, first column. So to get that element, we're using this second row, this first column. First element by first element, second element by second element. First element by first element, second element by second element. 0 times -1 and 2 times 0. 0 times -1 and 2 times 0. 0 times -1 is 0 and 2 times 0 is 0. So that value there is 0. And this last element down here now is in the second row, second column. So to get that element, you have to use this second row and this second column. First element by first element, second element by second element. First element by first element, second element by second element. 0 times 3 and 2 times 2. 0 times 3 and 2 times 2. 0 times 3, 2 times 2. 0 times 3 is 0, 2 times 2 is 4. That's that. So this reduces to 3, 2, 1, 4 minus, this becomes 1, this becomes 3, this becomes 0, that becomes 4. And then you're subtracting the corresponding values now to get the final matrix. So it's 3 times 1 is 2. Not 2 times, sorry, not times. 3 minus 1. 3 minus 1 is 2. And then 2 minus 3 is -1. 2 minus 3 is -1. And then 1 minus 0 is 1. and then 4 minus 4 is 0, and therefore this right here is the answer for part A of question 1, part A. All right, we're going on to part B. Part B next. Part B next. So that's the part B over here. So we're going on to question 1B. All right, so question 1B is this one right here. This one, that one. And it says that matrix M is singular. So if it is singular, then we know that it has no inverse. The determinant is 0. So they gave us this matrix M is the matrix X, 12, 3, X. And I said that it is singular. Remember, singular means it has no inverse. That's one. And the second thing is that the determinant of M is equal to 0. And this thing here is what you use for your calculation. So that's what we're going to use on here. Determinant of M is equal to 0. So let's write that the determinant of M is equal to 0. So we need to write an expression for the determinant and express it as 0. And some persons still getting it wrong. The determinant is this product minus, not plus, not multiply, minus product of those two values. Product means you multiply them. Some persons adding them and putting 2x, and some persons adding these two values. No, pay attention to the details. It is the product, means that you multiply them. The product of these two values on the first diagonal minus, not plus, minus the product of these two values on the second diagonal. You multiply them. So it's x times x, which is x squared, minus, let me write the product, 3 times 12. Let me write it. Instead of just write 36, I'm going to write 3 times 12. That's the determinant, and it is equal to 0. So this equation becomes x squared minus 36 equals 0. And so we can transpose the 36 and get x squared equals 36. Then to leave x as a subject, we need to get rid of the square. The inverse of square is the square root. So we're going to have to square it both sides. But when we square it both sides, we have to consider that it can be plus or minus. And what can help us to know is that the question said values. So it means that is more than one value. All right? So that again is important. So it means that x equals plus or minus square root of 36. X equals plus or minus 6. So x is equal to positive 6 or negative 6. Why? Because remember, positive 6 squared is 36, and negative 6 squared is still 36. All right, so that's why the answer is either plus or minus 6. Some persons write it like this: x equals 6 or x equals negative 6. So those are the possible values, 6 or negative 6. All right, and that is that. All right, so that is question 1B. Moving on to question 2. So question 2. So question 2 now is your typical question where they give you a pair of linear simultaneous equations. All right, so they give us a pair of linear simultaneous equations. Even though it's a matrices question, it was a pair of simultaneous equations. So it's 2x plus 5y equals 6 and 3x plus 4y equals 8. Those are the two equations. Part one in the question wants us to write it in a matrix form. Ax equals b. Right? So in other words, sometimes I write this and sometimes I don't write it. They just write it in a matrix form. It's the same thing. Right? It doesn't matter. So write it in a matrix form. So in a matrix form, you have to always ensure As I said, you have the x value followed by the y value in the two equations, which is good in the first one. And in the second one, you have the x value followed by the y value, which is good in the second one. You always want to check that. Since that is the case, you know that in the matrix form, it's going to be a 2 by 2 matrix times the column matrix xy equals a column matrix 6, 8. All right, the xy is from the two equations there. And you have the x followed by a y, that's why you have them down there. And then the 6, 8 is from here, that you get. All right, and the question said right, you know, question said right. Right, so it means that you don't calculate anything, just write it down. And you're gonna fill in this now. When you fill that in from the coefficients up here. So it's 2, 5, or the coefficients of the x and y up there. 2, 5, 3, 4. 3, 4. This one easy because all the values were positive. So there's no negative to consider. And basically that is the equation for part 1. All right. So in essence, this is your A, this is your X, and this is your B. So if they refer to A, they're talking about this one. If they refer to X, they're talking about this one. If they refer to B, they're talking about that one. Based on what they said. Because they said they wanted AX equals B. All right, then we'll come to part 2. So part 2 now. They want us to calculate the determinant of A. All right, and a common mistake is for persons when they calculate the determinant of A. This is the matrix A now. They do 1 over and calculate it under here. No. The determinant is the determinant, not 1 over. You use 1 over the determinant when you're forming the inverse. So I think one person did this. And it's a common mistake because everybody's so used to writing 1 over the determinant. 1 over the determinant times the adjoint when they're doing the inverse. If you ask them for the determinant, they want to give you this. No, that's not the determinant. The determinant is the leading product, leading diagonal product, minus the following diagonal product. So don't do that. It is this product. It is this product minus this product. One person did the sum. So one person did 6 minus 8. That is wrong. They use a sum. But they do, they add them and get 6 and add these 2 and get 8. That is wrong. All right. Some other persons, I'm showing you the mistakes, right? Some other persons add the products. So some other persons did 8 plus 15. No, it's minus. You're supposed to have minus. All right. So try not to make those mistakes again. In any case, it is, remember, this product means multiply, minus, not plus, minus this product. So call it the first diagonal product minus second diagonal product. So it's 2 times 4. Let me write it out for you. 2 times 4 minus 3 times 5. And that becomes 8 minus 15. And so the determinant is -7. Some people got 1 over -7, which is wrong. This is the determinant. When we're doing the inverse, we put that in front of the adjoint, right? But pay attention to the details. Pay attention to the details. All right? So that is your determinant. All right? The determinant of the matrix is -7. Part B. Part B says calculate the inverse, a to the -1. So the formula for the inverse, a to the -1, is 1 over the determinant now of the A times the adjoint of A. All right, so you put in the values now. So it becomes 1 over the -7 multiplied by the adjoint. How do we do the adjoint now? Interchange the elements on the first diagonal. Interchange them. So the 2 and the 4 interchange to become 4 and 2. Then the other 2 elements on the following diagonal, they stay where they are. Don't interchange those 2. Leave them where they are and just change the sign. And so you get a -5 up here and a -3 down here. See, they stay where they are and change sign. When you say change sign, it means if it is negative, it becomes positive. If it is positive, it becomes negative. both of them positive in this case, and so both of them become negative down here. All right, and then now it's a matter of dividing each value by the -7. And can remember that negative over negative is positive, so you don't have to put like -5 over -7. All right, so as I said, this is the inverse, you know. So if I'm going to do any calculation, I'm going to use this for the fraction outside. But in writing the final inverse, I'm going to divide by the -7. So I'm going to get 4 over -7. I'm going to get 5 over 7 because the negatives cancel. I'm going to get 3 over 7 because the negatives cancel. I'm going to get 2 over -7. So that is my a to the -1 matrix, my inverse matrix of a to the -1. But if I'm going to do any calculation with a to the -1, I'm going to use this. And invariably, these questions, you will always have to do some calculation with the inverse, because you're always testing your knowledge of using the inverse to solve the equation. So questions always ask you that. All right, then we'll come to part C now. It says, see, telling in part C, it says use the inverse to solve for x and y. So we're solving the equation. So let's see where we start. We're starting back is that if you have the ax equals b, remember the ax is the x and the y now, then the x that you want as a subject becomes a to the -1 in front, a to the -1 in front of the b. Why is that? Let me show you why is that. Because remember, we multiply in front both sides by a to the -1. These two is your I matrix. And the I matrix times x is just simply equal back to x. That is what is happening behind the scenes. We don't need to show what is in red. Right? And then leave out that step and show that final result. That is why the a to the -1 go in front there. That's why it goes to the front. All right, that's it. So based on that, then the xy that we want, sorry, remember the x is the xy, right? From up here. See here. So the xy that we want, which is xy, is equal to the a to the -1. But as I said, we're going to use this one, the fraction outside. So it becomes 1 over -7 times the 4, -5, -3, 2. That's our a to the -1 right there. We're multiplying it by b. Remember the b is 68. 68. That's it. So we're going to calculate this part first. Leave the 1 over -7 for last. We're calculating that, use the rows of the first matrix with the 1 column, because there's only 1 column. All right. So this calculation becomes that xy is equal to 1 over -7. Now calculating to get a column matrix, 2 values there and there. First value here is the first row, 1 column. So we use this first row with the 1 column. So it's a 4 times the 6 and the -5 times the 8. 4 times the 6 minus 5 times 8. 4 times 6 minus 5 times 8. 4 times 6 is 24. Minus 5 times 8 is -40. And this element down here is second row, 1 column. So second row, 1 column. So it's 3 times, -3 times the 6 and 2 times the 8. -3 times 6, 2 times 8. -3 times 6, 2 times 8. -3 times 6, 2 times 8. -3 times 6 is -18. And 2 times 8 is 16. 2 8 is 16. 2 8 is 16. And so your xy becomes equal to 1 over -7. Or 24 minus 40 is -16. And -8 plus 16 down here is -2. And so now you're going to divide each of these now by the -7. And again, the negatives will cancel. And so xy, I know still must like big people, no man, but I put negative, the negative over the negative when them actually cancel. I always carry them down to the lowest terms. So I don't want you to put negative 16 over negative 7. When the negative is obviously cancel. Don't leave it like that, man. Do the math like big people. So it becomes 16 over 7 and 2 over 7, because the negatives cancel. And since the question asks for x and y, you have to actually write the value for x and the value for y. So from this, you're going to say that the x, therefore, is 16 over 7, and the y is 2 over 7. And you hardly get questions where you get fractions as the answers in these, but it happens from time to time, right? So you cannot feel uncomfortable when you get that. And what you can maybe do is test these values back in the original equation up here. Test them in the original equation to see if they work. All right, but I'm not going to test it now. I know that they work, and I've actually showed you how to test them already. All right, so that is the question. That was the classwork. Nice and easy question. All right, so I promised you that I would show you something. That there are times when you have to multiply the inverse on the other side. I'm just going to show you this one time, and hopefully you can understand. All right, and then maybe closer to the exam or later don't revise, we might touch it again. Just at CSEC, I've never set any question with it. But suppose we had a matrices equation, right? Where instead it was, x a equals b. And I'm not saying that unless both of them are 2 by 2 matrices, right? All right, let me write it. Let me write AB equals C. Suppose I have a matrix equation like AB equals C. And let's say that it is the A that I don't know. So for example, an equation like an equation like A, B, C, D. So that one I don't know, times 1, 3, 5, 4. And let's say that equal to another matrix, 0, 1, 2, so negative 1. That's just making up something. I want to find these values. Obviously, it's set out different. The ones that we've been doing so far is the one where the thing that you're trying to find is right here. All right. And you want to, so in this area, let's deal with this one. So in this case, you want to get rid of this because you want to leave this as a subject. To get rid of this, you have to multiply its inverse beside it. Right? You have to multiply its inverse beside it. So let's look back at this A, B, and C so we can illustrate it. So let's look back at this A, B, and C. So it's A, B equals C. I'm trying to make A the subject. So I'm going to put a question sign over the A, as if to say it is A that we don't know. So I'm going to put a question sign. This is the one that we don't know, the A in front. So because we don't know A, I need to get rid of the B. To get rid of the B, I'm going to use the same principle that a matrix times its inverse equals the identity matrix. So in that case, this is the case I'm trying to make A the subject right there. Right? I would have to multiply both sides. I would have to take this side and multiply it by B to the minus 1 here. Because I use this to multiply by B to the minus 1, I have to also use this and multiply by B to the minus 1. So the B to the minus 1 also would have to come here because matrices multiplication is non-commutative. But understand that? So because I use this side to multiply B to the minus 1, I also have to use this side now to multiply B to the minus 1 in the same order. When it was AX equals B, and then this is what I don't know. I'm trying to get the A to the minus 1 beside that. So what I do, I multiply the A to the minus 1 beside it here. So I'm multiplying A to the minus 1 times this. So now I have to multiply A to the minus 1 times the B. In the same order, the same direction, because matrices multiplication is non-commutative. So it's A to the minus 1 times the left side, and a to the minus 1 times the right side. Up here now, it would be, up here now, it would be the left side. Up here now, in this example, it will be the left side times b to the minus 1 and the right side times b to the minus 1, because matrices multiplication is non-commutative. So therefore, you have to multiply them in the same order. So since I take this side and multiply it by b, I have to use this side and multiply it by b. In this example, I'm taking a to the minus 1 and multiply this side. And then on this one, I'm taking a to the minus 1 and multiply that side. Hope everybody understand what I'm doing, you know. So let me get back to the core of what I want to do. I want to illustrate you. And CSEC only did this once. And no, they have not done it in an exam, but they do it on the specimen paper. So basically, I'm saying you have to multiply the left side by b to the minus 1 and also multiply the right side by b to the minus 1. And then what is going to happen now is the same thing. Same thing, which is that this b times b to the minus 1 is the identity matrix. And therefore, it reduces to A times the identity matrix. Let me use about the red. The equation reduces to A times identity matrix equals C times B to the minus 1. And then anything times I. Remember, the I is just like the matrix 1. In that case, the A would be equal to C times B to the minus 1. So in this case, now you're multiplying the B to the minus 1 second. In this case, you multiply the B to the minus 1 second. Right? And that is if I start with, look back up here, I started with this up here. AB equals C, where it is the A that I don't know. Let me underline the unknown. It is the A that I don't know. So I'm trying to make A the subject. See there? So if I'm doing this question right here now, let's go back to this. If I'm doing this question, this question, then what would happen is that my A, B, C, D would be equal to the, think of it, I would have to multiply this matrix on this side by its inverse, and would therefore multiply this side by the same inverse. All right, and then these two parts will become I. Just think of it that way. And so the inverse have to go on the right side. All right, so that it will become equal to 0, 1, 2 minus 1. That's this side times the inverse of this would have to go all the way over here. Inverse would have to go all the way over there. All right, so you multiply that by the inverse 1, 3, 5, 4 to the minus 1 to the minus 1. That's what you have to do. And then you will get A, B, C, D equals 0, 1, 2 minus 1. And you run the inverse now. 1 over the determinant, which is this product minus this product. That will be 4 minus 15. 4 minus 15. 4 minus 15 times the adjoint. Interchange these two. So you get 4 and 1. Leave these two where they are, change the sign. Minus 3, minus 5. And you could still leave the fraction for last, but you back out the front because it's just a multiplying factor, and you multiply these two matrices. And then when you finish, you get the value for A, B, and C. All right, anybody understand that? This should become A, B, C, D equals, this should be 1 over negative 11. So I put this at the front, and I'm multiplying 0, 1, 2, negative 1 times 4 minus 3 minus 5, 1. All right, and then I'm multiplying these two. Get a matrix, divide each of them by the negative 11, and then I would know the A, the B, and the C. All right, and 6, you don't set any question like this yet, where the unknown is in front. No, they have never done it. They will put on a specimen paper. It has always been like this, where the unknown is second. I say multiply both sides in front by A to the minus 1. And then these two becomes the I matrix. All right. Any questions there? Anybody understand that? I just explained. Hello.
Yes, sir.
Yes, sir. Yes, sir.
Yes.
Understood.
All right. Cool. So just that 60 don't send any questions there, but we'll address it again closer to the exam, and maybe in the revision, just so that persons remember. So if the unknown ever comes in front, they know that you have to multiply the inverse second behind it. You have to multiply the inverse here to get rid of this b. All right, so that you can leave the a as a subject if the a comes in front. All right, enough of that. So I want to get to the transformation. So as I said, we're gonna do the transformation in about notes part in about 3 or 4 classes. So I'm just gonna do some of it today, some of it tomorrow, some of it Wednesday, and then on Sunday we'll do a class activity. If we go fast enough and I feel like persons are comfortable, then I might actually just do the class activity on Wednesday. So get your geometry set and everything by Wednesday, just in case I decide to do the class activity on Wednesday. All right, but that is the plan right now, really. All right. So it is now time for our transformation. Right. Nicest topic in maths. All right, transformation geometry. So what is transformation? When a geometric object, a point, a line, a curve, or a polygon, any geometric object changes its position, meaning it moves from one place to another, changes its orientation. Orientation refers to how the letters go around the object, changes its shape, or changes its size, like it gets smaller or it gets larger. It is said to be transformed by one of the processes of transformation. Let me explain orientation. I think maybe orientation is the one person might not understand fully. So, like if I write A, B, C on this object, it means that it has a clockwise orientation because the letters are going around the object in a clockwise direction. I write another triangle and I write A, B, C this way, then it has an anti-clockwise orientation. So orientation has to do with how the letters go around the object, right? Or you label the points around an object. You can generally use that in reference to orientation. All right, so that's what we're going to be using for our orientation. So if the orientation changes, it also has gone through a transformation. All right, and we're going to see which transformation does that. Actually, reflection in a line changes orientation. So any change that a geometric object makes, including geometric objects are points, lines,
Sir, mic mute.
all right, students, sorry about that. All right, so that is that. So the original object, the object I was starting with is most times called the object, is most times called the object. But the proper name for it really is the pre-image. Proper name for it is pre-image. All right, but we're gonna mostly be calling it the object, the original object that is transformed. The resulting object, the object that we get after we perform the transformation, is called the image. The image. I'm going from scratch, and I'm going from scratch, right? And I'm assuming that you know what image means, or object means, or pre-image. I'm going from scratch with this thing. All right, whether you know it before or not. So the object that you have originally is called an object or pre-image, and the resulting object is called the image. And we say that the pre-image maps onto the image, or you might say the object maps onto the image. The object maps onto the image. All right. When an object is transformed by one of the processes of transformation, and this is important, if the entire object goes under a transformation, it means that each point on the object undergoes the same process. So it cannot be that you have an object like a square, go through a reflection, and then you're thinking that a point on the square go through a different transformation like a rotation. No. If the object goes through a transformation, then all points go through the same transformation. So generally speaking, if you can decide what transformation took place on a point and an object, then you know that the entire object would have gone through that same transformation. All right, so this can be important. So each point on an object goes through the same transformation as the entire object itself. All right, so that is why sometimes we can just go to a point to know what the transformation is. All right, for the purpose of calculation, in transformation, we're going to be transforming points in the XY plane, right? That are usually written like that. For the purpose of the calculation, we're going to be using the column matrix for the purpose of the calculation. This is the column matrix right here. Hold on there. Hold it. Right. Marker has gone bad. The pen. All right. So pen just gone bad. Hold on a second, guys. All right. All right. So basically, what I'm saying is that, generally speaking, you will carry out transformation of points in the XY plane. Points like this. But for the purpose of calculating, you're going to use a column vector for the point like this. So if you're doing a calculation on a point that is 3, 4, when you're doing the calculation, you're going to be using the vector 3, 4. I want to ask a question, if anybody have an idea why. So let's say I'm going to be transforming a point, and you're going to be using some 2 by 2 matrices to transform points. So for example, let's say we're doing a transformation using the matrix 0, 1, 1, 0. We'd have to multiply the matrix by the point. But why is it that we can't use a point like this? Instead, we'd have to use it like this. We have to use a point like this to do the calculation. We can't use it like that. Anybody can tell me why I would have to use it like this? Anybody can tell me why?
Sir, because in order for multiply, sir, you need the same number of rows in the first
Columns.
matrix. Columns.
Columns to
Columns
match
in,
the rows.
yes, sir.
So it comes back to how multiplication is possible. If you use this one, the second one, you are correct and you're saying the right thing. But we're doing a 2 by 2. I'm multiplying this now by a 2 by 1. 2 by 2 and a 2 by 1. So it's possible because this is 2 and this is 2. So it is possible. If you're doing it this way, then you basically be trying to do a 2 by 2 and a 1 by 2. Because it would have 1 row and 2 columns, right? Using a column, using a point like that. 1 by 2. Because this number of columns does not match that number of rows, then this would not be possible. Not possible. And that's why when we're doing calculation with points in vectors and also in transformation, we use the points as column vector. That's what we call a column vector. So if we're doing a calculation at point -1, 6, we use a column vector for the calculation, -1, 6. I know that this is the x value and this is the y value. All right? And that's what this basically is saying down here. That's all that this down here is saying. Right here. That is what that is saying. All right. Good. Going from the basics. Explain everything. All right. Let's go into the types of transformation now. So there are 4 types of transformation that is left on your syllabus. There used to be a 5th one in the past called a share. Would have taken off the share of the syllabus. And you're now only using the 4 that I'm going to show you. I'm going to maybe look at 3 of them today. We're also going to do some compound transformation, just similar to composite functions. So the compound transformation is similar to the composite functions. I remember the transformation and the functions kind of similar. There are a lot of similarities, and you see them as we go. What are the types of transformation? There are 4 main types that we're going to look at. Right? They remove the share and they have left us with translation. That's the first one we're going to deal with today. Very easy. All of them very easy. Translation is represented by the letter T. Normally, it's represented by the letter T. All right, not all the time. Normally, we're going to deal with reflection. Reflection has to do with a mirror line, and that's why it is represented by the letter M. M really is for mirror line. So reflection is another type of transformation we're going to deal with, and is usually represented by the letter M. Then we're going to use rotation. Because they're using R for rotation, that's why they have to find something different to use for the reflection, and so they go for the M. So the R is used for rotation normally. And the fourth one we're going to deal with, we're not going to do this one today at all, is the enlargement transformation. So if you see the word size there, the correct name really is enlargement. And the reason why some people call it size and don't call it enlargement is because a lot of students, because it is called enlargement, they feel that it is only when something gets larger. No. Whether the object gets larger or smaller, the transformation is still called an enlargement. And that's why some persons just simplify it and say, okay, a size transformation. So it has to do with the change in size. So as I tell you now, whether the object gets larger or smaller, the name of the transformation is still enlargement. You more than likely will see the word enlargement on your exam. You're not going to see size on your exam paper. They would more than likely use the word enlargement and enlargement transformation. If the thing get bigger, it name enlargement. If the thing gets smaller, it still name enlargement. Don't create any name for yourself for any of these transformations. So if they ask you to describe a transformation, it must be one of these or a combination of these. It must be one of these or a combination of these. Remember, the one that we're using for the size is really enlargement. All right, so this is the one that I want us to see. What determines if it gets larger or smaller is something that we call a scale factor. Right? So for example, if the scale factor is a half, then the thing becomes half its size. If the scale factor is 2, then it becomes twice its size. And the scale factor can be positive or negative as well. But when we get to enlargement, we'll deal with all those things. But I just wanted to emphasize that from now. So even if the object gets smaller, it is still called an enlargement. All right? Just wanted to point that out from now. All right. So we're also going to be dealing with inverse transformation. So just as though we have an inverse function that reverses what a function did, an inverse transformation reverses what an original transformation did. And a lot of the times, the inverse transformation is a common sense thing, right? If a transformation do something to a point or to an object, the inverse will reverse what it did and take it back to its original state or original position. That's the inverse transformation. So it's common sense like, right? And that's how the matrices come in now and the inverse matrix come in. Because matrices can be used to perform transformations, and therefore the inverse of a matrix will reverse any transformation that an original matrix did. And that's why you have to be able to calculate inverse matrices. All right. So we're also going to look at compound transformation. And compound transformation, as I said, is sort of similar to your composite functions in a similar kind of way. We're going to see the similarities later. And then there's a special kind of compound transformation that we're going to look at. It's called a glide reflection. But we're going to deal with the glide reflection later down, far down in this thing, maybe Wednesday. We're going to deal with the glide reflection. All right, simple stuff, you know. Don't think any of this thing complicated. We just have to do it in stages. So we're gonna get to the compound transformation and the glide reflection in the next class, maybe tomorrow or Wednesday. We'll get to that. But we're gonna deal with these 4 basic ones first, and then we'll look at the compound and the conditions under which the compound can work. All right, because you can't just form a compound randomly. There are certain certain conditions under which compound transformations can work and stuff. So we're going to look at those. All right, and a shortcut way to get the compound transformations. All right, and you have to pay attention to them and know them. And they're in the must know sheet. All of them, all of what I'm telling you will be in the must know sheet. So after I explain them to you, then you use your must know sheet for revision to solidify the information and keep it in your head. And then remember everything important. So you have to pay attention to all the minute details. All right. So the first one is a translation. It's the simplest one. And it is one that has to do with moving an object from one location to another. Translation. You don't turn the object, you don't change the size, you don't trouble the orientation. Just move it without turning or anything. Just move it from one location to another. And that is translation. Translation. So a translation is a transformation in which an object changes its position without turning, right? Also, and without changing size. Make a note for me here. Make a note for me here. And without change in size. All right. So right here, you're going to say and without. So those of you who have your handout can write it in there for me. Without change in size. So all that happens is that it changes position from one location to another. No change in size and also no change in orientation. Without changing size and without changing orientation. You can write that as well. So it just changes position from one location to another. The movement of the object is generally broken down into the two primary Cartesian directions. The two primary Cartesian directions are the x direction and the y direction. Those are the two primary Cartesian directions, and they break the movement down into those two primary directions. X units horizontally and y units vertically. Y units vertically. Right? It is represented by a column matrix. The translation is represented by a column matrix, AB. All right? So the A is the number of units horizontally, and the B is the number of units vertically that the object moves. All right? Now we're talking about all of this in the XY plane. We're talking about moving in the XY plane, X-axis and Y-axis plane. We're talking about movement horizontally or vertically. That's what we mean in the XY plane. So therefore, in the case when a translation is 4-3, as what I'm looking at here now, this example right here, right? When it is 4-3, like that, then what will happen is that the object will move 4 units to the right. That's in the X direction, 4 units to the right. That's what I mean. So we're gonna move 4 units this way. The object will move 4 units to the right. That's because it is positive. And the 3 means that it's also going to move 3 units upwards. 3 units upwards. 3 units upwards. All right. It's going to use 4 units to the right and 3 units upwards. Suppose the values are negative. What does the negative mean? A translation, for example, that is t equals -5, -6. The -5 means 4 units to the left, because you're moving in the negative x direction now. So the -5 would mean 5, not 4, 5 units. 5 units this way. 5 units this way. And the -6 would mean downwards. So you move 6 units downwards. 6 units down here. 6 units downwards. So that is it basically. So the first value in the matrix is always the horizontal movement. Right? So the first value is always horizontal movement. Positive means it goes so, negative means it goes so. The second value is always the y movement, vertical. Positive means you move up, negative means it moves down. Negative means down. Simple as that, almost commonsensical. All right, 5 units to the left, that's horizontally. 6 units downwards, that's vertically. All right, pretty straightforward. So let's look at this triangle. We're going to perform a transformation, a transformation. So it's a transformation. It is a transformation, but this is a translation, transformation. We're going to perform a translation on the triangle. So let's look at the triangle. Let's look at the triangle. So the triangle moves some units to the right and some units upwards. So what we have to do first is locate the corresponding points on the object and the image. So what happens now is that this now is your object that you started with, and this is your image. So this is your object, and this is your image of the translation. Huh?
Instead of object, wouldn't you say free image?
Yes, but I'm just using pre-image and object interchangeably because object is what you're going to see mostly in the exam questions. Object is going to go with what is a term you're going to be using mostly, but you know that the scientific name for it is pre-image. So just keep that in your mind. Don't lose the word pre-image out of your mind, even though we're going to be saying object all the time. You understand? But pre-image is the scientific name for it. So if you're doing a question say pre-image, you know that they're talking about the object. But more than likely, the question will say the object. Believe me, more than likely it will say object. All right. So the object is usually referring to what we had before, but they'll always use the word image for what we get afterwards. All right. Object and image. All right. Good question. All right. Then we're going to put on the points, the corresponding points. So these are the corresponding points. And the corresponding points on the image are usually shown with the prime on the letters. You can see the prime on the letters. That's how they do it. They put the prime on the letters. So for example, A prime, you can see it right there. B prime, C prime. So A prime is the image of that point. B prime is the image of that point. And C prime is the image of that point. If they move this object to another location, then the letters will now become double prime. So you get like A double prime, B double prime, C double prime. That means it's a second transformation that took place. If they move that again, then they go to the triple prime, A triple prime, B triple prime, C triple prime. You'll hardly ever get a case where you're gonna do having a triple prime. Most times you go from an object to one image and then a second image. Most times they don't generally go to a fourth. All right, a fourth object or a fourth shape. So basically that's what we have. All right. So the important thing now is that if we're going to describe this transformation, you're going to look and observe it. You're going to look and see that there's no change in the size. That's one. There's no change in the size. There's no change in the orientation. Look at it. ABC is this way. ABC is this way. There is no turning. What do you mean by there's no turning? There's no turning because this AB is horizontal. This AB is still horizontal. This AC is vertical. This AC is still vertical. So there is no turning. There's no change in orientation. There's no change in size. There's no turning. All that took place was the object moved from one location to another location. Then what is also important is that you have to identify movement by observation of the corresponding points. One mistake people would make, for example, is to focus on the movement from here to here, which is wrong. No, B didn't move to B to A prime. You have to realize that the movement is actually from B to B prime. And you count how many units across and how many units upwards for B prime. If you're going to use C, same thing. How many units across, how many units up to C. If you're going to use A, then it's how many units from A across, how many units up to A. So the convenient one, so you're not interfering with the object, would be B to B prime. And I don't need to do it for all the points. I only need to do it for one point. Why? Because the transformation that took place on the entire object, same transformation took place on any of the points, any one of the points, same transformation. So I just need to look and see what happened to B, and I'm good. So B moved 1, 2, 3, 4, 5 units to the right. See there, 1. Let me write it out so you can see it. B moved 1, 2, 3, 4, 5 units to the right, and then it moved 1, 2, 3, 4 units upwards. 5 units this way, 4 units that way. So I know that it's a translation 5, 4 that map ABC onto A prime, B prime, C prime. So it's 5, 4 is a translation. All right, so let's look at what the slide is saying. So in the diagram, triangle ABC is mapped onto A prime, B prime, C prime by moving 5 units to the right, 4 units upwards. And I say you don't focus on the entire object. Use 1 point. Look at what happened to 1 point. 1 point. And B, as we said, move 5 units to the right, 4 units upwards. It has to be B to B prime. So this transformation is therefore a translation given by T equals 5, 4. So if you have to describe it, that's all you have to say. The transformation is a translation given by T equals 5, 4. Now, we can also do it using calculation. So we do it by observation, or we can also do the points by calculation. So let's look at it by calculation. All right. So for calculation, when the transformation is a translation, you add the translation matrix to the matrix for the point. It is the only one that you add. Translation is the only transformation that you're adding to the point. All the others you'll be multiplying by a 2 by 2 matrix. I'm gonna see that later. So this is the only one that we add. So the point A plus the translation gives us the point A prime. That's what that is saying. And then you put in the matrix for the points now. That's it. So you see that the point A was a point 2, 2. But you can see that A is 2, 2. But because A is a point 2, 2 right here. But we're gonna do the calculation, we use the matrix like that. And the translation is this. And you add the values, you get the coordinates of A prime. And you can see that the coordinates of A prime right here is actually 7, 6. See there? 7, 6. And then you do that for the calculation. And then once you finish with the calculation, you can put on the points like that. So A22 mapped by translation T, see there, mapped by translation T onto the point A prime, which is 6, 7. And then it's the same calculation for B. Same thing for B. See there? That's it for B. B is a point 6, 2. It go under the translation 5, 4 to the point 11, 6, where B prime is located. I can represent it like that. C is similar sort of thing. C plus the translation matrix, take it to C prime. C is a point 2, 5, 2, 5 like that. Translation is 5, 4. You add the values, C prime goes to 7, 9. 7, 9. So you can write it like that as well. So it's a similar sort of thing. But good so far? That's translation.
Yes, sir.
Yes, Dad.
All right. Very good. All right. So we'll look at now inverse translation. So tell me now, common sense. If translation 5, 4, we cannot use common sense right here. If translation 5, 4, take me from this to this. What is the inverse of that transformation? What is the inverse? What will be the inverse, guys?
-5, -4.
Very good. -5, -4. Can you just reversing what you did? So you're coming back and you're going back down. Simple as that. You're going back 5 and come back down 4. So the inverse of a translation is a negative translation. Simple. This one is common sense. So I don't even want to spend too much time on that. So you're just going to subtract. But the inverse of any transformation, as we said, is a transformation that returns the image back to the object, back to the original position. So this in red is for any transformation. So because it's the first time I'm introducing the inverse, I just wanted to tell you what the inverse of a transformation is. The inverse of any transformation is the transformation, is another transformation, that will map the image back to the object, the image of a transformation. In the case of a translation, the inverse is negative, the negative translation. As I just saw, it's almost common sense. See there? So on the transformation, 4, 3 is a different one now. This is 4, 3. A while ago we did 5, 4, I think. 5, 4 over here. So using a different one now, 4, 3. I'm not going to spend a lot of time on it because you get it. Is a minus going to take you back. One thing I'm going to show you here is that when you want to perform a transformation on multiple points at the same time, like A, B, and C, instead of doing them one at a time, as we did in the example on the previous page over here, we did them one at a time, right? We did a calculation for this, calculation for this, and a calculation for that. We could have put the 3 of them in one matrix, right? Put the 3 of them in one matrix like this. A, B, C. It's not really a 2 by 3 matrix, you know. It's really a 3 column matrices in one. So it's just 3 column matrices. I put the 3 of them in one just to speed up the process, right? And then I put the first matrix 2, 2. So this is a column matrix for A. Then the column matrix for B would be 6, 2. The column matrix for C would be 2, 5. Why can I do that? Because I'm performing the same translation on all of them, right? I'm performing the same translation on the 3 of them. And put the T up here. I'm performing the same translation on the 3 of them, which is 5, 4. And this is going to be equal to A prime, B prime, C prime, C prime. And again, it's really 3 single matrices just represented in one matrix. So it's not really a 2 by 3 matrix, this, you know. It's really 3 column matrices together in one. So it was a quick way of doing the calculation. And so I would get my 7, 6 right here from my A prime. I'll get my 7, 6 right here from my A prime. I would get my 11, 6 right here from a B prime, and I will get my 7, 9 right here from a B prime. So we can do it that way, right? So instead of doing it in 3 separate calculations, we do one calculation with all of them in it. And I know that my A prime is still 7, 6. My B prime is still 11, 6. And my C prime is still 7, 9 from here, from this one, and this one. But understand that? So this is a quick way of putting all of them in one in the column matrix. It's just convenient to do it that way. All right, so that's what you're seeing over here now. So you have those 3 points. Instead of putting 3 separate calculations, we'll put one calculation like that. So it's really 3 matrices in one. So let me use a red line for here. So I'm separating them. 3 matrices, 3 matrices. So I don't want you to view it as if to say it is one matrix. Right? I don't want you to view it as if it is one matrix. Draw them back. So there's 3 separate matrices in one. All right, so it's just a convenient way of doing it. All right, and then you can still get the image points like that from it. And what we are saying is now the inverse matrix on the other page will reverse it and carry it back, which everybody figured out already. The inverse, if you subtract now the image, see there now the image points minus t, see, minus t, going to take it back to the object. All right, which is common sense almost. So put on the matrix again, 3 in 1, subtract the t and get the 3 in 1 back to the object. So it takes it back to the object once. All right, so the inverse of a translation t is minus t, as Kai said. If it was 4, 5, it's going to go to the inverse is minus 4, minus 5, because it reverses what was done before. And that's translation in a nutshell. Done with translation right there. Just need to do questions with it now. Very easy. It's the only one that we're adding values. All right. Next one we're going to look at now is reflection. And reflection have some common sense in it too, you know. All right. And we can relate to reflection. But why? Because we look in mirrors every day. So the same thing that happens with a mirror that we're looking every day in the real world is the same thing that is happening here as well. Right? It's the same concept. So reflection applies the same concept of what happens when you place an object in front of a mirror, right? And you get that image. It's the same concept, really. That's what this is saying. So reflection is a transformation which applies a concept of an image that is produced when an object is placed in front of a mirror. So think of it. If you go close to the mirror, your image comes close to you. If you go far back from the mirror, then the image is also stepping back. And so we know that the image distance will always be equal to the object distance. The next thing is that your right hand is like your left hand in the image. And so you have a reversal of the orientation, because the right hand is like your left hand and the left hand is like your right hand. The right side appears to be a left side and so forth. So there's a reversal of the orientation. If you turn your back to the mirror, the image turns back to you. If you face the mirror, the image faces the mirror. If you turn to your right, the image looks as if it is turning to the left because it's facing the same side. Right? So the orientation is reversed. It's like it's turning in the opposite direction. So if you are turning in one direction, the image looks like it's turning in the opposite direction. All right? Orientation is reversed. So the result of reflection of an object in a mirror line is called a mirror image. So because we're talking about the image produced by a mirror line, the term that they use is mirror image. Mirror image, right? So all of these is like semantics. And the important thing, as we say, is that the mirror is like a line of symmetry between the object and the image because the distance is the same and so forth, right? So it's like a line of symmetry. So look at this example now. So of the triangle ABC, I'm going to place that like that is a mirror line. So you know that the image is going to be the same distance on the other side of the mirror line. And it's going to be oriented the opposite direction. So A is the furthest distance from mirror line. So the image of A is going to be furthest distance on the other side. B and C are the same distance, closer. So the B and C on the image side also going to be closer. So the image is going to look like that. Right? And if you observe, the orientation is reversed. So look at the object, ABC is clockwise. If you look at the image, ABC is anti-clockwise. And I can tell you from now, reflection is in a mirror line is the only transformation that reverses orientation. It's the only transformation that reverses orientation. So if you're ever doing a transformation question and you're looking at an image and an object, and you can't see what transformation it is. And a lot of the times, the rotation and the reflection will look alike. It look like it's just, you will see a reflection and look like a rotation. And you see a rotation, it look like it's a reflection. To decipher which one it is, you can just check the orientation. If the orientation is reversed, as it is in this case, then you know definitely it is a reflection that you have. It's a reflection in a line that you have. Because reflection in a line is the only transformation that reverses the orientation. And we can see, because we can just think of when we stand in front of a mirror, the orientation is reversed. The image between the image and ourselves, orientation is reversed. All right, so that is it. So two things that happens with a reflection in a line. Orientation is reversed, very important. This thing is very, very important. That orientation is reversed. Very, very important. Key to solving a lot of questions in deciphering whether we have a rotation or a reflection. Orientation is reversed. And then the next thing is that the object distance and the image distance on the mirror line is the same. Perpendicular distance we're talking about. From the object distance and the image distance from the mirror line will be the same. All right, so that's it. Those are the properties of your reflection. All right, those are the properties of your reflection. All right, so let's perform reflection with this thing now, and you'll be required to perform reflections in the exam on graphs. Now, important thing is that when you're going to perform your reflection or any transformation for that matter on a graph, don't try to do the transformation on the entire object all at once. Do it one point at a time. This is very important. Let me say it again. Don't try to transform the entire object all at once. Don't try to draw the image all at once. Just transform each point, one point at a time. And when you have all the points in place, then you draw the image. Right? So do it one point at a time. And remember that it is object distance equals image distance, or the image distance is equal to the object distance. So let's say I'm going to transform this triangle. I'm going to do a reflection in the line x equals 7. So that's my mirror line. I'm going to do a reflection in the mirror line. Do it one point at a time. So do A first. So the image of A is going right there. Image distance equals object distance. Good. Then B, let's count off B. B, if you look at it, it is 1, 2, 3, 4, 5, 6 to the mirror line. So it's going to go 6 on that side. Let me use the red and make it clearer. So the B is 1, 2, 3, 4, 5, 6 units to the mirror line. So it's going to go 6 on the other side. 1, 2, 3, 4, 5, 6. So the B is coming right there. Let's look at it. That's it. Then C is 2 from the mirror line. So it's going to go 2 on the other side. That's it. Now that you have the point in place, that is when you draw the triangle. Don't try to reflect the entire triangle all at once. Do it one point at a time. Remember, you're going to have to do this for me either Wednesday or Sunday. You know? So that is it. So that's how we reflect in that line. And you see that the orientation reverse because we reflected in a mirror line. So this one is anti-clockwise, A to B to C. No, that is clockwise. But on this one, A to B to C is anti-clockwise. You can see it. A to B to C is anti-clockwise. The orientation is reversed. Let's also reflect in the x-axis. Let's also do a reflection in the x-axis, this line. I'm going to do a reflection in the x-axis now, this same one. Same concept. Image distance equal object distance. Let's do the point A first. So A is going to go 2 on the other side. Then B is also going to go 2 on the other side. Let me show the mirror line. I will reflecting in this line now. This line. All right, reflecting in that line. So B is going to go there. Then C, count C. C is 1, 2, 3, 4, 5 on the mirror line. 5 from the mirror line. Let's show it. See it here? 1, 2, 3, 4, 5 from the mirror line. It's going to go 5 on the other side. 1, 2, 3, 4, 5. So it's coming right here. That's where it's going. That's C going right there. All right. So we can draw that. Put that point there. That's it. Now that the points are in place, then you draw the triangle. Going slowly with this thing, you know, because everything important. And then you see also again that the orientation is reversed, right? So A to B to C, and this one is clockwise, and this one A to B to C is the opposite way, anti-clockwise. Why? Because we did a reflection in a mirror line. We did a reflection in a line right here. We did a reflection in that mirror line. So the orientation is reversed. All right, good. That's your reflection. All right, and that is that. So far, so good. Nice and easy. Going slowly, you know, or jump into anything. All right, I think we're going to introduce our matrices now. Bam, or reflection matrices. All right, so let me tell you about the matrices now. The matrices, so what we did a while ago on this previous slide was to actually just count the points and do the reflection by actually constructing it by observation, doing one point at a time. The matrices will actually calculate, the image points for you. That's what the matrices do, the reflection matrices. So there are matrices for reflection, there are matrices for rotation, there are matrices for enlargement. We are now focusing on the matrices for reflection. And there are set number of matrices that you're supposed to know for certain specific lines, and also the origin that you're supposed to know. I can show you how you can work them out, but it's a waste of time to work them out. It is better for you to just take the time, study and learn them. I'm not talking about 10 matrices. I think it's just 5 matrices for reflection, maybe 2 matrices for rotation and 1 matrix for enlargement. So it's easy to just learn those matrices. Just know them, study them, and know them. Easier. I'm going to show you, I'm going to also prove to you why it is good enough to just know them. I'm going to show you how to work them out, you know. But it's easier to just know them. All right? So let's look at the reflection matrices now. So the common reflection matrices that I use to calculate the image of points when you reflect are the ones that are the ones for when you reflect over the x-axis, when you reflect over the y-axis, when you reflect over the line y equals x, when you reflect over the line y equals minus x. Let me just show you those lines quickly. I'm not taking anything for granted. So this is the y-axis, this is the x-axis. So if I have a point here, this is my y-axis, this is my x-axis. Let me put a point here instead. If I have a point here, there is a matrix that will calculate. There's a matrix that will calculate. Let's say this point is 1, 5. 1, 5. If I reflect this point over the x-axis, anybody can tell me where it's gonna go? That point is 1, 5. Tell me where this point will go if I reflect it over the x-axis. It's gonna come down here. What will be the coordinates of this point down here? If I reflect over the x-axis, what will be the coordinates of that
Sir, it will
point?
be 1, -5, sir.
Beautiful. 1, -5. So I'm telling you now is that there's a matrix that will calculate that this point will go from here to here if I reflect it over the x-axis. That matrix is the x-axis reflection matrix. Good? And that matrix, I can write it down for you. It is 0. No, not 0. Not 0. That is wrong. Erase that. That matrix is 1, 0, 0, -1. That is that matrix. 1, 0, 0, -1. And let me prove it to you. If I multiply 1, 0, 0, -1 by the point 1, 5 and calculate it, what am I going to get? I'm going to get 1 times 1 and 0 times 5, right? 1 times 1 and 0. I forget that I can't think there now. I can't undo with this thing. I forgot I cannot undo. All right, let me use this down here then. Let me use something else. I just want to show you. Let me use this down here. Right, so I'm doing the matrix for x-axis, and we agree that's gonna go to 1, -5. So the matrix for effective over x-axis, I tell you now, is 1, 0, 0, -1. So what I'm saying to you is that if I use that x-axis matrix, reflection matrix, and I multiply it by the point 1, 5, remember we have to use a column vector and do the calculation. That calculation is gonna tell me my answer. It's going to tell me this answer down here. It's going to tell me that my image is this point down here, right? The 1, -5. So see it here now. If I multiply this out, the 1 times 1 and the 0 times 5. The 1 times 1 is 1 and the 0 times 5 is 0. So you see that this value is actually 1. And then for the value down here now, it's going to be this times this, which is 0, and -1 times 5. It's -5. So you see that? That will become -5. So you see that this matrix does the calculation for you. That is the point that I'm trying to make. The matrix does the calculation for you. Why is this thing going there? Hold on a second. Hold on a second, guys. I don't know why this thing come up, you know. All right, come back to this now. Do you understand that so far? So the matrix for reflecting over the x-axis shows you that it is proven that that matrix will do the calculation for you. And so the matrix that represents a reflection of the x-axis is this one. Let's look at another one, just for argument's sake. Tell me where the point would go over here now. Same point. Tell me where it would go if I reflect it over the y-axis. Where would it go? It's going to come over here. What is the coordinate of that point? Look at it. If I reflect this over this point, what will be the coordinate of this point right here?
-1, 5.
-1, -1, 5. I can show that. So if I reflect over the y-axis, so let's look at the y-axis one now. Let's use a different color for the y-axis one. So I'm telling you now that the y-axis one, the y-axis matrix is -1, 0, 0, 1. And I'm telling you now, if I use that matrix and multiply the 1, 5, it's going to give me the image point, which is -1, 5. Look at it. Because the -1 times the 1 is -1, and the 0 times the 5 is 0. So see that actually giving us -1 here, right? And then the 0 times 1 is 0, and the 1 times 5 is 5. So it's giving us 5 here, right? So it means that this is a y-axis reflection matrix. It will reflect points over the y-axis. This is the x-axis reflection matrix, this one, x-axis. It will reflect points over the x-axis. So when they ask for the matrix that represents a reflection over the x-axis, they're talking about this one. When they ask for the matrix that represents a reflection over the y-axis, they're talking about this one. And then there's a matrix for this, and then there's a matrix for that, and there's a matrix for reflecting through the origin. Those are reflection matrices, and let me write them down for you now. So you understand how the matrices work. I just did those two examples to show you how the matrices work. But understand that calculate those so far, that's how the matrices work. The matrices are used to actually carry out the transformation for you that you're describing. All right. So let's write them down for you. So these are the matrices. The x-axis one is that. And that's what it will do. That is what it will do. Let me show you how you know what it will do to a general point. So the xy right here that I have represents a general point, all points. Let me show you how you can work out what it will do over here. So if I have the matrix 1, 0, 0, -1, which is the x-axis reflection matrix, and I multiply it by a general point xy, I'm going to see what the result will be. 1 times x and 0 times y is x. Then 0 times x is 0, -1 times y is -y. So you see that matrix, the x-axis reflection matrix, 1, 0, 0, -1, which is the x-axis reflection, will map a general point xy onto a point x, -y. But you don't have to memorize this, you know, you can always work it out. You don't have to memorize this. Okay, I can always work it out as I did right here. You can always work it out as I just did right here. It's not coming up over that side. I don't know why it's not coming up over here. Anyway, it's not coming up over here. But as I just worked it out here, you can always work it out. You get me? You can always work it out like that. So I don't memorize these. I don't try to memorize these. I don't try to memorize that. Because I can work it out. What I memorize is the matrix. I can always work out this by just putting xy beside it. Let's put xy beside it right here. I'll work it out if I want. Right? And I find that there's no need to memorize this over the years. What I need to memorize is this matrix. Also need to memorize that matrix. And the next matrix to memorize is the 1 over the line y equals x. That one. That one now reverses x and y values. Remember what we did functions, and we said the relationship between a function and its inverse is a reflection in the line y equals x. And what happens when you do a function and its inverse, the x and y values reverse. Remember that? Hope you can remember from functions. So we see in the connection, the x and y values reverse when reflecting the line y equals x. And we said that was the relationship between a function and its inverse, a reflection in the line y equals x. So we're seeing some of the connections now. In line y equals minus x. We're reflecting line y equals minus x. That's what we get. Let me draw the line so you can see that. So we know the y-axis and the x-axis. I just want everybody to be clear on what we're talking about. So we have the y-axis and we have the x-axis. y-axis, and we have x-axis. So everybody know these two, first two, right? Those two, y-axis and x-axis, those two. The line y equals x now is a line that goes right down the middle here, y equals x. And it passes through points where the x and the y value is the same. So it passes through points like 0, 0, that's a pass through the origin. Pass through a point like 4, 4. Pass through a point like 8, 8. Pass through a point like -3, -3. You pass through points where the x and the y value is the same. That's a line y equals x. Let me draw a line y equals minus x in a different color now. So y equals minus x is at 90 degrees to this line and go this way. That's line y equals minus x. I don't want anybody to be working blind. So this is the line y equals minus x. So this one pass through points now where the x and y value is the same value, but when one positive, the other one negative. So you pass through points like, for example, 2, -2, and 4, -4, or -3, 3. So they have the same value, but when one positive, the other one negative. So another one here, -5, 5, for example. That's the line y equals minus x. And the matrix are reflecting in the line y equals minus x and line y equals x are these two matrices now. Bam and bam. Those two. So I'm not marking. Those two. And we have to learn all of them. We have to know them. And there's an easy way to memorize them. I'm going to show you the easy way to memorize them that I use. I'm going to show you the easy way that I use to remember them. There's also reflecting it through the origin. There's also reflecting through the origin. Now, the reflecting through the origin, I look at it as a combination of these two in one. Two of them in one, give me this. Because we're going to learn later on that two reflections over the y-axis and the x-axis is equivalent to a reflection to the origin or equivalent to a 180-degree rotation about the origin. So it's the same matrix. See there? Same as a 180-degree rotation through the origin. So a reflection over the x-axis and a reflection over the y-axis is the same as a 180-degree rotation through the origin. And so both matrices are in the same one matrix, both of them in one. So you see the negative one that is up here is here. And the negative one that is down here is there. So the two of them in one, both of them in one. And the reason why I see it as that way is because my way of memorizing the matrices is to remember where the negatives are. I remember where the negatives are. That's how I memorize these matrices. My method of memorizing them is a method I call follow the negative sign. Follow the negative sign. And it's quite simple, you know. If you know this one, then you automatically know that one because they interchange. And if you know this one, then you automatically know that one, this one. And if you know these two, then you automatically know this one down here. That's how I memorize them. But let me show you. Let me write out all of them and show you now. Quick and fast. Those reflection matrices. Watch this. Let me write them out and show you how I memorize them. All right. And you need to take some time to remember them. But before I write them out for you, let me give you an example of why you need to know them. Let me give you an example. So you don't think that I'm just telling you to know them for no reason. Let me give you an example of why you need to know them. Let me show you. All right. Let me show you. Let me show you why you need to know them. I'm going to give you an example of why you need to know them. I'm going to show you two past paper questions so you can see for yourself. Transformation. Here is it. Homework. Watch this now. I'm going to show you a couple questions so you can see it for yourself. So these are past paper questions, right? These are past paper questions. All right. I'm going to show you a couple examples. Boom, 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 boom. All right. Watch out. Look at this one right here. Look at this question right here now. These are past paper questions. I'm showing you why you need to know them by showing you a question that I asked in the exam. Look at this one. That's an exam question, you know. So it's a Write down the 2 by 2 matrix R for reflection in the y-axis. See that? So that one would be the y-axis reflection -1, 0, 0, 1. That would be the answer. You know? Why waste time and work it out when the question says write it down? Write down means don't calculate nothing, just write it down. In order for you to write it down, just know it and write it down. Look at this one. Look at the second one. Write down a 2 by 2 matrix N for a clockwise 180 degree rotation about the origin. That's the one that I showed you over there. The 2 negative, -1, 0, 0, -1. That's the answer. Look at this one now. Write down a 2 by 1 matrix translation. This is representing translation -3 parallel to the x-axis, 5 parallel to the y-axis. That is t equals -3, 5. You know? That's it. Easy 3 marks if you just know the matrices. So these two you have to know. This one you can work out because I gave you the values, the -3 and the 5. Let me show you another example. Right? I show you that I'm not joking. Why it is important for you to know them. So that's one example, one here. I said that. Let me show you another one now. All right. Show you another one. It's another here. Look at this one. It's another example here. This is another example. See there? Write down the 2 by 2 matrix for reflection in the y-axis. See there again? -1, 0, 0, 1. Write down the 2 by 2 matrix for reflection line y equals x. See there? 0, 1, 1, 0. That's it. You know? Just write them down. And then we're going to learn later on how to do that. All right? I'm just showing you that they actually ask you these things in exam. All right? Look at this one. All right, so here I wanted to write down these matrices. Write down these matrices. Transformation G, transformation M, transformation G followed by M. That is because over here, I told you what G was and what M was. See there? M was a reflection line y equals -x. So the reflection for that one is 0, -1, -1, 0. That's that. Right. I know you don't know them yet, but I'm going to show you. I'm just showing you why you need to know them first. That actually after those in exams. Right? This one is an enlargement matrix. I think the scale factor was 2, so it will be 2, 0, 0, 2, or -2. Right? But that would be that one, I think. All right, I'll show you the other one. Look at this one. Write down the matrix MY for reflection in the y-axis. Same thing again. -1, 0, 0, 1. RL represents rotation 180 degrees about the origin. -1, 0, 0, -1. So my whole brain can know them, and you can know them. So look at this one now. Describe geometrically transformation represented by this. So I said that want to know what matrix that is. So give you the matrix. Which one is that? That one is an anti-clockwise 90-degree rotation about the origin. We don't do that yet, but that's what that is. Anti-clockwise 90-degree rotation about the origin. That's what this one is. And then this one now, this one is an enlargement of scale factor 2 about the origin. That's what that one is. You have to learn the matrices. So you see the question give you the matrix and want you to tell them what it is. See there? Describe the geometric transformation represented by that and that. So you have to see the matrices and know what they are. You don't want to waste time and work it out. Have to work it out in an exam. No, just learn the matrices. Just learn them, know them. Right? Q and R, look at this one again. Q and R are 2 transformation, that and that. See there? Describe them. The more you describe them, see them there? Describe transformation Q and R. This one is a reflection in line y equals -x. This one is a reflection in x-axis. That's it. You have to learn them, right? You have to learn them, guys. So I'm showing you exam questions. These are all exam questions where you're testing your knowledge of them. Right? Look at this one up here. Write down the matrix M and so order. Describe the transformation. The transformation here, reflection line y equals x. And I'm supposed to write down the matrix for it. That matrix is 0, 1, 1, 0. Reflection line y equals x. All right, and then do a combination. We're gonna do this next, well, maybe tomorrow or Wednesday. L followed by M. We're gonna deal with that tomorrow. So don't worry about that yet. But I'm showing you with these examples why you have to know them, because these are questions CSEC ask you. right? They give you the matrix and ask you to describe them, or they ask you to write down the matrices. Write down some of these standard matrices that you must know. It's another one here. See there? Write down a 2 by 2 matrix. See there? Right here. Write down the 2 by 2 matrix R for a reflection line y equals x. Right? That is 0, 1, 1, 0. It's another one here. Write down 2 by 2 matrix for anticlockwise rotation 180 degrees about origin. -1, 0, 0, -1. That's that. And then it's about describing words what this means. This transformation right here. That's a translation, you know. 2 units to the right, 1 unit downwards. See? Translation matrix, that you know. That's a translation transformation. So in this case, Q is a translation. This one is a translation that we just looked at. 2 units to the right, 2 units to the right, 1 unit downwards. So this would move an object 2 units this way and 1 unit down to there. 2 units to the right, 2 units to the right, 1 unit down. That's what this will do. So it's a translation. So I'm just giving you some examples of why you have to learn the matrices, guys. So you have seen it for yourself. They ask these things in the exam. They expect you to learn and know them. And I'm telling you, when you know them, question get easier. Even if they don't ask for them, these are the matrices they will give you. And if you understand how the matrices work and you know them, that's why I tell you, you can know the answer that you're going to get for a question based on some other things that I'm going to teach you, right? That you can actually know the answer that you're going to get. All right. So I've shown you why you need to learn them. So let me show you now how I remember them. Let me just show you how we know how I remember them. I'm just going to show you the reflection one time. I'm going to show you how I remember them, how Mr. Shaw remember them. And you can adapt my method of remembering them. It works every time. My method is a method I call follow the negative sign. So I remember where the negative is in each of the matrices. Now, if you look at the matrices carefully, they have the ones and the negative ones are always on the same diagonal. Always on the same diagonal. So in other words, if you have a 0 here, so you must have a 0 down there. So if you have a 0 here, so you must have a 0 here. So if you have a 1 here, so then you're going to have a 1 or a -1 over there. So so the ones are always on the same diagonal. If the 1 is over here, then it's have the -1 or the 1 down here. So, but the zeros are always on the same diagonal. That's the first thing. All right. Now you also have to know which of the matrices have 1 negative in it and which one have 2 negatives in it. All right. Them easy to remember. All right. So the first matrix I remember is the y-axis reflection matrix. I always remember that one in my head first. The y-axis reflection matrix. Because it has the first -1 in it. That's the first one I remember. The y-axis reflection matrix is one with the first -1 in it right there. First -1 in it. That's it. And so the 1 is down here, 0, 0 there. That's my y-axis reflection matrix. If this is the y-axis reflection matrix, then the x-axis reflection one is easy because I just interchange the negative and the 1 up there. So the x-axis reflection is easy to remember now. The x-axis reflection is easy to remember. So I just make sure that we know the y-axis one that has the first -1 in it. And therefore, I also know the x-axis one. X-axis reflection one. And the negative, the 1 and the negative interchange place. That's the x-axis reflection. Easy like that. Then know the y equals x1, the y equals x matrix, the y equals x reflection matrix, y equals x reflection matrix. You know why I remember this one? Because it's the one that looks like the identity matrix. Remember that the identity matrix, you know, is 1, 0, 0, 1, you know. Starts with a 1. The y equals x, it has 2 1s in it, but the ones are on the other side, here and here. So see there? It looks like the identity matrix, but it's not the identity matrix. The ones are on the other diagonal. That's it. Y equals x reflection. If I can remember the y equals x reflection, it's easy to remember the y equals minus x, because in the y equals minus x, these two become negative. Easy. So the y equals minus x, y equals minus x reflection matrix. Reflection. those two become negative. So I get 0, -1, -1, 0. And that's it. And then for, yes, good. And then for reflecting through the origin, which is the same as a 180-degree rotation, I combine these two. This is a 180-degree rotation. And about the origin. 180-degree rotation about the origin. About the origin. Which is the same as a reflection to the origin. Reflection. Let's call it origin reflection. Same as a origin reflection. Reflection through the origin. Can reflect through a point, you know. Can also reflect through a point. A reflection to a point is the same as a 180-degree rotation about the point. A reflection through a point is the same as a 180-degree rotation about the point. We'll look at that later. But I can just tell you that from now. So this is the origin reflection. Reflection. Those two combine. So -1, 0, 0, -1. So the -1 that is here goes there, and the -1 that is there goes there. Both of them combine. Because later on, we're going to learn that two reflections over intersecting lines equivalent to a rotation. Twice angle between the lines. So if you reflect over the y-axis and then reflect over the x-axis, is equivalent to having a 180-degree rotation. Got the two of them in one. Two of them in one. That's it. Those are my reflection matrices. Easy to remember. There's 5 of them. Easy. And I start by memorizing the first one that has the first -1 in it. The y-axis reflection one is the one that has the first -1 in it. If I know the y-axis one, then I automatically know this one. This one, I remember that it looks like the identity matrix. Right? The identity matrix, the ones are here. The ones are here. 1, 0, 0, 1. This one, the ones are on the other diagonal. See there? On the other diagonal. For that one. Easy to remember. Easy. Right? So remember this one, as I said. I remember this one by remembering the identity. The identity matrix. And then now, if I know this one, I automatically know that one. But these two positive ones become negative ones. For the y equals -x. So they're easy to remember. And then now I combine these two up here, as I said, to get that one up there. Combine those two to get the 180-degree rotation, which is same as reflecting to the origin. Let me show you the rotation ones now. Easy, I can just show them from now. And this is rotation about the origin. Rotation about the origin. All right. So rotation about the origin. Rotation, meaning that the origin is the center of the rotation. About the origin. These are the matrices now. Same thing, I follow the negative sign. So the first one, I put the arrow up here, so it means that is an anti-clockwise 90-degree rotation about origin. This arrow up here tells me that the negative one is at the top. And a 1 down here and a 0 there. That's my anti-clockwise 90-degree rotation matrix. So remember this. Anti-clockwise rotation. Tell me that the negative one is at the top up here. Anti-clockwise 90-degree rotation. So for my clockwise 90-degree rotation now, the negative come down here because it go down to the next end. -1, 1, 0. That's for my clockwise 90-degree rotation matrix about the origin. Done. Those are the two of them. Easy. Those are the two. I already know the 180. The 180 is this. I already know the 180. That's the 180 rotation, which same as reflecting to the origin. So that's a 90-degree anti-clockwise, 90-degree clockwise. Easy. And then for size or enlargement is K00K. That's enlargement about the origin. About the origin. We're going to come to these later, and I'm just going ahead of time. This is an enlargement about the origin of scale factor K. Scale factor K. So the scale factor is 2, then it's 2, 0, 0, 2. The scale factor is -1/2, there's -1/2, 0, 0 minus half. Simple as that. Scale factor always go right here and here. Enlargement about the origin. Them easy to remember. And they're on the must-know sheet, guys. They're all on the must-know sheet. All right? So those are the matrices. Now, let me show you how you can calculate it if you don't memorize it, which is far more difficult. Believe me. It's much, 100 million times easier to remember them than to waste time and calculate them. So I'm going to show you how you can work it out. All right? A procedure to work it out. Watch this. Over here. So the way to work it out is to use points that you will know what the transformation is. So we use a point 1, 0 on the x-axis, and we use a point 0, 1 on the y-axis, because we know what the result of any transformation of those 2 points will be. 1, 0 on the x-axis and 0, 1 on the y-axis. So let's say I'm trying to find out the x-axis reflection matrix. I'm trying to find it out. I don't know what it is. So I'm going to set it up so I can find it out. So as I said, I'm using the point 0, 1 on the y-axis and 1, 0 on the x-axis. Now I know if I reflect this point in the x-axis, because it is already in the x-axis, it's going to stay exactly where it is. So the image of that point is the same point. Because if you put your finger on a mirror, the image is also on the mirror. If you put your nose on a mirror, then the nose is also on the mirror. So the reflection distance is 0. So the image distance is 0. So the image and the object is the same point. It's called an invariant point. An invariant point is a point that does not move under a transformation. So we're going to see that word again later. So when you reflect on when you points on a mirror line are invariant points, because when you reflect points on a mirror line, they stay exactly where they are. So they are invariant points because they stay where they are on the mirror line. All right. So if you reflect a point on the x-axis, it's going to stay on the x-axis. So this first point is going to stay same place. All right. So that's what we know. And then this point, this other point up here, if you reflect it in the x-axis, if you reflect the x-axis, it's going to come down here to 0, -1. We know that. We know what it's going to happen. So we use points that we know what will happen. All right. So that's the premise on what we should do it. So as we are saying, that point is going to go back there. See, put back the 1, 0. And then the point 0, 1 is going to go down to 0, -1. So we know what the result of those 2 points will be if we reflect in the x-axis. So we use that knowledge. Then the matrix, because we don't know what it is, we're assuming that we don't know what it is, we call it A, B, C, D. That's what we do. We call the reflection matrix over the x-axis A, B, C, D, because we don't know what it is. But what we definitely know is that if we apply the matrix A, B, C, D to the point on the x-axis, which is 1, 0, we know that the answer is going to be 1, 0. So we're setting up an equality of matrices. We also know that if we apply the matrix A, B, C, D, which is a reflection over the x-axis that we're trying to find, and we apply it to the point 0, 1, which is the point on the y-axis, the image is going to be 0, -1. We know that. And then all we have to do now is work out which row and which column will give us this value and set up an equality of matrices. That's what we have to learn those things, So we're basically setting up 2 equality of matrices here. But the reason why I use 1 point on the y-axis and 1 point on the x-axis is because the point on the x-axis is going to give you the A and the B, and the point on the y-axis is going to give you the C and the D. That's how it works. The point on the y-axis is going to give you the A and the B, and the point on the y-axis is going to give you the C and the D. So let's look back at the slide now, what happens. So that is what we're saying. We know that the point 1, 0 is mapped onto 1, 0 when you reflect it in the x-axis. But the point 0, 1 is mapped onto 0, -1 when you reflect in the same x-axis. And you say you set up the equality of matrices like that. And from the equality of matrices, we see that equation, right? Let me work it out over here and show you so you can see it. So we know that we take the rows of the first matrix. I'll do that. And we know that this row times this column equals the 1. That's what we know, So we know say A times 1 and B times 0 equals 1. That's what we know, That's how we get it. That's how we get it. That's how we get. That's how we get the A equals 1. Okay, you really get A plus 0 equals 1, which means the A equals 1. And then we know that this row times the 1 column equals this 0. You know that. So you know, say C times 1 and B D times 0 equals 0. So you're going to use that as well. So you know that C plus 0 equals 0. So you get the C equals 0. See there? C equals 0. So you get those two values. So you get the A and the C. You get two other values. You get the A and the C. And the other point is going to give you the B and the D. So I said it wrong. So the point on the x-axis give you the A and the C. The point on the y-axis give you the B and the D. Some other questions give you the other two, though. It depends on the points that you're doing. Right? It depends on the points that you're doing. But what I know is that the point on the x-axis is going to give you two other values in the matrix, and the point on the y-axis is going to give you the other two values in the matrix. So if you set up the other matrix, set up the other equality of matrices now, you're going to get that. It's the second one that we wrote. That's for reflecting the point on the y-axis now. And if you apply the same equality of matrices method, you get the other two values. And if you put those values now, these values in the matrix, you see what the matrix is. See the reflection on the x-axis matrix is that. But why go through all of that? You can just know it. Now in the slide that I gave you in the handout, I did it for all of them. If you like, you can reach all of them, but I'm not going to go through all of them because I don't intend persons to have to do this in the exam. When you can just know them, just know the matrices instead of waste time working them out. So I'm skipping through all of them. So you can look back at the notes, look in the notes, these are all in the handout, and you can see how they can be calculated, similar to how we did the first one. But why go through all of them? You can just learn them, just know them. That's it. All right, so we reach inverse reflection. Everybody good so far? How are we so far? Everybody all right?
Yes, sir.
Yeah. All right. So I'm gonna just do up some more. I'm gonna stop at some point. Let me see. Reflection. All right. I might just stop at the reflection today. I don't want to give it too much one. I might just stop at the reflection today. It's now 1 something already. So I stop at the reflection today and pick up back with the rotation tomorrow. All right, and then Wednesday we continue. So we end up maybe doing the classwork on Sunday. So because I wanted to revise some stuff today. I wanted to watch over the video, cement everything that I tell you. Today, start studying, start learning the matrices. Start learning the matrices. Right? Start learning the matrices. All right. Before we move on though, what do you think is the inverse of a reflection in a mirror line? So let me just set it up for you. So let's say I have a triangle like this. And I have a mirror line right here. The image is this. So this is A, B, C, and this is A, B, and C up here. So with the prime, this is my image. So I did a reflection over this mirror line M to go from this to this. Question is, what transformation is going to take me from this back to this? Common sense. If a reflection in this mirror line M takes me from this to this, what transformation is going to take me back from this to that? What can you tell me? Common sense. Look at it. Easy.
Inverse.
Reflection.
A reflection in the same mirror line.
Alright.
So if you reflect the object in the mirror line to go to there, you have to reflect the image back in the same mirror line to go back to that. Simple. So the inverse of a reflection in a mirror line is a reflection in the same mirror line. That's it. The inverse of a reflection in a mirror line is a reflection in the same mirror line. And that's what this is going to say. And since the same mirror line will reflect the image back to the object, then the inverse of a reflection M is also reflection M. Note that for all the reflection matrices, if you calculate the inverse of any of the reflection matrices, you're going to get the same matrix. So for reflection, for example, the one of the reflection matrix is negative 1, 0, 0, 1. That's a reflection for the y-axis. Y-axis, right? Is that. If you calculate the inverse of this matrix, which is the matrix that will reverse reflecting in the y-axis, you're going to get back the same matrix. So m to the minus 1 of the y-axis reflection is the same matrix, minus 1, 0, 0, 1. If you want to calculate it, you can calculate it. That means that the inverse of a reflection is the same reflection. Right? Because you see if a matrix, you see if a transformation matrix, A, B, C, D, move a point from P to P prime. Let's say this matrix move a point from P to P prime. Right? Then the inverse of this, which is 1 over the determinant times the adjoint. Let's call the matrix M. So this is a matrix M. What that matrix will do, it will move P prime back to P. Let's put it the other way. It will move P prime back to P. So I can put M on this. M move P to P prime. Then M to the minus 1 will move P prime back to P. All right, and we're going to see that later on. All right, I'm just giving you the information and I'm building up your knowledge on this thing. And we're going to go into specifics later on. I'm giving you the information. All right. All right. So last thing I want to finish off with now is reflection over parallel lines. Two reflections over parallel lines. So this is one of the things that you must know. All right. So let's look at it. Two reflections over parallel lines is equivalent to a translation. Twice the distance between lines. Two reflections over parallel lines is equivalent to a translation, which is perpendicular to the line and twice the distance between the line. So if you reflect over two parallel lines, two consecutive reflections over parallel lines, this is equivalent to a translation. The direction of a translation is perpendicular to the mirror line, and the length of the translation is twice the distance between the mirror line. Let's look at it. So let's say I have that triangle there, and I have those two parallel mirror lines. So M1 and M2 are two parallel mirror lines, and I have this triangle. And I'm going to reflect it over this line first to come to here. And I'm going to reflect over this line to go to there. All right, two reflections over mirror lines. So let's look at it. When I do the first reflection, I'm getting that. But I give it that. If I reflect over M1, I'm getting that.
Yes, Dad.
And then I'm going to reflect this one. I'm going to reflect now this triangle now over this second mirror line. So I get two successive reflections. So I'm going to do a second reflection like that. I'm going to get that. So if you observe now, the beginning and the end, you see that they're oriented the same way, and it's almost like you get by the same thing. Because a translation would take you from this to this. So that's what this is basically saying. So it is equivalent to one translation. See that? One translation. It so happens that the translation direction, if you notice, the translation direction is perpendicular to the mirror line. Everybody can see that? Translation is perpendicular to the mirror lines. Perpendicular to the mirror lines. And also the distance of a translation is twice the distance between the mirror lines. The distance of a translation is twice the distance between the mirror lines. So the distance between the mirror lines is 5 units. Then this is 10 units. The translation is 10 units. If this equals 5 units, then the translation is 10 units. So that is something you have to know. So two reflections over parallel lines is equivalent to a translation perpendicular to the mirror lines at the direction of the translation. And the size of a translation is twice the distance between the mirror lines. Twice the distance between the mirror lines. That is something that you must know. I'm going to do questions with it, but I'm not dealing with any questions yet. I'm going to start back tomorrow with rotation. Now, in the old days, I would normally do rotation today as well, but no problem. Online, we have an additional day per week. So I'm going to start back with rotation tomorrow. But before you go, right, let me show you what you need to start studying on the must-know sheet. Everybody's supposed to have this must-know sheet. Transformation must-know sheet right here. So let me show you what I want you to start studying. You must know between today and tomorrow. So this is the must-know sheet that everybody is supposed to know. All right. So we dealt with translation. What did we do already? We dealt with translation here. So start study that. Translation. All right. Don't do enlargement yet. But I want you to do reflection. See, and these are the matrices for reflection you're supposed to start learning, right? That we did today. So you're doing translation and you're doing reflection. Those are what I want you to study today. Start studying, start memorizing those matrices. And see, I put them in the same order that I memorized them in. Same order. Right? Well, this one come before this one still, but no matter, I think it's a space thing. I did that here. All right. So, reason I did that way, let me show you how I do that way. I'm saying if I memorize this one, then I memorize this one. Then these two combine to give me this one. And then if I can memorize this one, then I automatically know this one. Now remember that, as I said, this one, reflection line y equals x, is the one that looks like the I matrix. I matrix is 1, 0, 0, 1. But notice that the ones are on the other diagonal of this as compared to that. All right. And we already know the I matrix. So it's easy to know the y equals x reflection matrix. All right. So I want us to start studying those two sets, guys. That's your homework. Start studying these things. Start studying reflection. And can correct this for me. That's a reflection. It's supposed to be reflection. Correct that for me. And also start studying this up here, the translation. Start studying a translation. Study those two for me. All right. Make sure you know everything on those two. We're going to pick it up back tomorrow with this. And then we're going to jump to that. And then we're going to go down to the compound. All right. These compound. See the two reflections over parallel lines here that we just did. See here. See it? We just did that a while ago. Equivalent to a translation. The direction is perpendicular to the lines. The direction is twice the distance between the lines. So you can study that one as well. Let me mark it since we did it already. Let me mark this as something that you must start studying too. Start studying this one as well. Just study what we did already. Just, look over what we did. Watch about the video and stuff. Start studying that. We're going to deal with compound transformation and so forth tomorrow. Right? You can also maybe study the inverse. The inverse kind of supposed to make sense to you. Already the inverse. You can study this stuff. Right? That makes sense. Inverse matrix will do the opposite of what the matrix did. All right, so that's that. So study those that I've marked. Make a note. Right, so you're gonna study. Let me take this out. You're gonna study translation, study reflection, study inverse transformation. Those are the component yet. Study those for me. And you're gonna study two reflections over parallel lines. We're gonna explain this one and so forth. This one, we're gonna explain all of that tomorrow. All right, so don't worry about the rest of it yet. You'll get the rest of them. So study those for me, guys. All right, so even though I introduce you to the rotation matrices, don't worry about them yet. We're gonna deal with them by themselves tomorrow because I want to focus on this. Oh, there's one last thing I want to tell you before you leave is that there are questions that will ask you to describe the transformation, right? From time to time. And there's a special way that you describe each kind of transformation. If you're describing a translation, you have to give how many units here to describe. I'm telling you what you have to state if you're describing a translation. You have to describe a translation by stating how many units the object moved left or right, together with how many units it moved up or down. That is how you describe a translation. That's what that's saying. If you're going to describe a reflection, to describe a reflection, you basically have to state the mirror line, state the equation of the mirror line. If it's a reflection to a point, you say like a reflection to the origin. All right. Note also, remember that for reflection in a mirror line, the orientation is reversed. Orientation is reversed. So all of that. But just remember though, if you're describing a reflection, you have to state the mirror line. You have to state the mirror line, the equation of the mirror line. Oh Lord, oh Lord. All right. If you're describing a reflection, you have to state the equation of the mirror line, or state the coordinates of the point. And if you're describing a translation, you have to state how many units left or right and how many units up or down. And you can also sometimes give the matrix. If there's something got 3 units to the right and 4 units down, you write 3 negative 4. Something like that. If you got 3 units to the right and 4 units down, you can write that. All right. You have to state the components. To describe it, you have to state the components. Because the question won't, for example, just say, describe the translation. It's going to say, describe the translation fully. Describe the reflection fully. If it's a rotation, we're going to learn that you have to state these 3 things: direction, angle, and center. That is for tomorrow. So don't worry about that yet. So study these things for me. I'm not going to give you any questions to do yet. Just study those things. When we finish the notes and stuff, then we'll get to questions. I just want to start studying these things. Please and thanks. I erased the reflection. Please, I erased it. All right, that's it. Study those things for me. Everybody good?
Yes, sir.
Yes,
Yes,
Dad.
sir.
Yeah, study those things until tomorrow, taking it step by step. I'm going to turn you into masters of this topic. All right, you're going to master this topic when I'm done with you. When we finish, you'll be able to do any transformation question, because trust me, they're very easy. They're very, very easy. All right, so study those things for me, and that's it. Any questions?
Yes, sir.
Yeah.
Sorry, but we're going to find the recording.
We're going when the recording is gonna. I'm gonna put the recording in the group. It's be available maybe in the next half an hour or so, and I put it in the group. And you go and watch it on Zoom. That's the only place you can watch it. You know, you have to watch it on the Zoom side. You're not allowed to watch those videos anywhere else. That's how it is. So I'm gonna share the link with the group. I'm gonna
Okay,
share the
sir.
link with the group, and you just go and watch the video, so you can look back over what we did today. All right. Don't get caught behind, ladies and gentlemen. Stay on top of things. So make sure you look back through the video. Make sure you understand everything that we spoke about today before we're moving on to new things tomorrow, and everything important. All right. It's a very easy topic, but you have to make sure that you know the things. The more you actually know, the easier this topic is. The more you know, the easier it is. That's why we have this must know sheet. Because the more you know these things, the easier questions will be to do. That's why I said, tell you, you can know the answer for a question without doing anything. Just by reading the question, you can know what the answer is going to be without doing anything. Just know what the answer is by knowing these things. So I need to take time and learn these things step by step in stages. All right. So start learning them from today, for me, please. If I can know them, you can know them too with my old brain. All right. So that's it for today. We'll pick it up back tomorrow, and we'll continue tomorrow with the rotation. We're gonna do rotation and enlargement. And depending on how far we get to, we might do the compound transformation on Wednesday and start doing some questions. And then we'll have a class activity to do. So let me just show you that. Remember, everybody need to get these pages printed. If you don't have it printed, if you have the booklet, then clearly you don't need to get it printed. So it's a class activity. All right, everybody need to get these pages printed.
Excuse me, sir.
Yes.
How can I get the booklet?
To get the booklet, when you register, get the booklet at KC.
Okay.
When you register, get the booklet at KC. So other persons who like persons out of town and stuff, I send these files to you directly. But this one you have to print it. This is in the booklet. But those who don't have the booklet will have to get these printed, because we want to perform all of these transformations. All right? They will have to be performed. And that's how we solidify the knowledge of the transformation transformation topic by going through these questions. Right, we'll go through these
Sir, which
questions.
page of the booklet are these on?
Just look in the transformation section, man. Just go to the transformation and turn through the pages. You see them. They come back to back to back in the booklet. They're in the booklet. All right. The handout that says CSEC number 2 or something like so, or CSEC number 1, that booklet. Those of you who went to KC and register and got the booklet, you see it in there. Those of you who didn't, you have to print it out. You have to get these pages printed. Okay, you have to actually do the transformation. I'm going to take you through it. We're going to go through the steps, step by step, how you do it, and you will understand the topic much better after we finish these. And this is for either Wednesday or Sunday, depending on how far we reach with the notes. All right? Cool? So those who don't have it, get it printed before Wednesday, please. You don't need it tomorrow, but definitely need it maybe by Wednesday. All right, that's it for today, guys. That's it for today. But good?
Yes,
Yes, sir.
Yes, sir.
All right, then that's it. So just do what I tell you and you'll be fine. Just do what I tell you and you'll be fine. Study what I tell you to study, know what I tell you to know, and you'll be good. Trust me, you'll be good.
So can you write now, right?
Yeah, man, we're good now. So I'm going to end it
All
now
right.
for everybody. All
Yes,
right,
sir.
bye, everybody.
Bye, sir.
Bye, sir.
Bye. Bye-bye. Bye, Kai.
Yes, sir.
Bye.
All righty. All right, I'm going to end it now. Bye, everybody.
Thanks for the class.
Yeah, man, cool.